This is the screencast for section 9.1, example 1. Now we're going to study power series in this section, but before we define what a power series is, we're going to look closer at a more specific type of power series that you dealt with in pre-calculus, the geometric series. So bear with me for a couple of examples where we look at geometric series before we show you how that relates to power series. So a geometric series is an infinite series in the expression of the form a1 plus a2 plus a3 plus a4, etc., or the sum from k equals 1 to infinity of a sub k. Now these numbers are terms in the series. So the partial sum would be maybe you're adding up one term or two terms or three terms or then four terms, five terms. Eventually you end up n terms. A partial sum is the addition of n terms. Now when we add up all the terms, infinitely many terms, and we get an actual number, that sequence has a limit and it converges. Otherwise, if we get just a bigger and bigger and bigger and bigger number, then it would diverge. So in example 1, we're going to look at a divergent series, and then in example 2, we'll look at a convergent series, and you'll be able to see the difference. So example 1, does the series 1 minus 1 plus 1 minus 1 plus 1, you get the idea, converge? Well, let's take a look at, first of all, that series itself. Now you might think, oh, sweet, 1 minus 1, 1 minus 1, 1 minus 1, those are all 0. So wouldn't I get 0 plus 0 plus 0 forever and ever and ever, and then that would converge? Well, actually, no. Unfortunately, that does not work. See, if there's an infinite number of pairings, the associative property of addition doesn't work. You can only use that for a finite sum. So like if I asked you for the first 10 terms, yeah, that would be 0. But if I keep going infinitely long, the sequence of partial sums would be like so. So the sum of the first two terms would be 0. But then the next one, if you add the third one in, would be 1. Add the fourth one in, 0. Fifth one would be 1. Sixth one would be 0, 1, 0, 1. And you'd keep going forever and ever and ever. You don't ever get to the same value. So, since the sequence has no limit, the series has no sum, therefore the series diverges. It doesn't have to go to infinity diverge, it just doesn't go to a single value. Also, the terms of the series don't approach 0, therefore the series diverges. Think about that. If you're going to add on something and keep adding and adding and adding, if you want to actually get to a finite sum, those values would have to approach 0. Eventually, you'd have to be adding on something so insignificant that it wouldn't matter. So since they don't approach 0, the series is going to diverge. Everything you add on is significant, changing the final sum. Then now try problem number 7. Compute the limit of the partial sums to determine whether the series converges or diverges. So partial sums, let's look at the sequence of partial sums. The first is 1, and then 1 plus 1.1 is 2.1. Now we're going to add the third one in, 3.21. Then we'll add the fourth one in, then the fifth one in, and then that would keep going forever and ever and ever, and you kind of see a pattern. This sum is getting larger and larger and larger with no sign of slowing down, no sign of reaching a limit. So since the sequence has no limit, the series has no sum and diverges. Again, we have a series that the terms do not approach 0. They're actually getting larger and larger and larger, technically. I mean, insignificantly larger, but with every term I add, the value of my sum is getting larger and larger, so the series will diverge.